Okay, last time we left at this point when we were starting to study what gravitational potential energy is. What is any potential energy? Any potential energy which is because of the field depends on the position of the observer with respect to the field, and gravitational potential energy is one of them. Uh, let's see if this is a large mass, a planet or a sun or any object, and this is the limit of its gravitational field, and not the actual limit, but we consider that this planet only has its gravitational field that till that line, because after that point the gravitational field because of this becomes, excuse me, so weak that we can simply ignore it. Let's make the mass smaller so it actually looks like that point is out of the field. Now, this is the central mass M. This is another mass M, which is outside the field. And this region is called infinity with respect to the central mass, because the object is beyond any significant gravitational field exerted by the capital M over here. Now, if we bring this mass from there to any point inside, so there was no gravitational field, and now this object has come from an outside field point, or outside field to inner field. This is a point where its distance from the center of the central mass is r. Now, what will happen? Let's consider smaller. So, what will happen to gravitational potential energy? Or okay, if you remember gravitational potential energy with respect to the planet, or the central mass that we are talking about, in our normal observation, the central mass will be Earth. So if we go away from Earth, what happens to gravitational potential energy? It
Decreases.
increases. It
Okay.
increases. But what happens if we come closer to the surface? The gravitational potential energy decreases. So you think that mass M has come from infinity to a point closer to the mass, so its gravitational potential energy should have decreased. And that is exactly the case. But see, how do we define gravitational potential energy? Amount of work done to bring an object from infinity to a certain point amount of work done to bring an object from infinity to a certain point in a field is called gravitational
Sir,
potential. Yes,
sir, you said the further you go, the what happens? Your energy increases.
yes.
Using which formula, sir? I don't get how that works.
Like if we lift something up, what happens
Yeah.
to gravitational potential energy?
Oh yeah, it increases. Khalas, okay.
Do you remember mgh?
Yeah, yeah.
And in mgh, we like actually mgh is not the formula for gravitational potential energy. In the end of today's lesson, we will learn that it is just the change in gravitational potential energy. It is not the gravitational potential energy, it is change of
The
gravitational
change.
potential energy. But in mgh, what we find is change of gravitational potential energy. And what we did in the previous classes, like in your O levels or IGCSE or AS, when an object rises, gravitational potential energy increases. Rise means what? Going away from the surface.
Yeah, yeah,
And falling means what? Coming towards the surface. And when object falls, it loses gravitational potential energy. So similarly, amount of work done to bring an object from infinity to a certain point inside a field, actually it should be gravitational field, is called gravitational potential energy of the object at the point. Okay, this is very important because we have mentioned a point somewhere before in the statement, and we are referring to the same point later in the statement. So we use the point. Now, if we bring an object from infinity to a certain point in the field, that work done is called gravitational potential energy. And the formula for gravitational potential energy, gravitational potential energy equals to minus G M M over R. Now, you would say, where does that minus sign comes from? Where does that minus sign come from? How is that minus is there? Like, let's put it as a question. Why
because it's
there is a negative sign with gravitational potential energies formula? Or, or the same question can be phrased as why gravitational potential energy is negative at any point inside a gravitational field. Now, pay attention. Why there is a negative sign with gravitational potential energy formula? That is one way of asking the question. And examiner sometimes says, why gravitational potential energy is negative at any point inside a gravitational field? Now, here is the answer. Gravitational potential energy is zero at infinity. Listen, if this mass has zero energy at infinity, it means like it is supposed to have zero energy because it is outside the gravitational field. Okay, it is supposed to have zero energy because it is far, far away and there is no influence of the gravitational field of capital M on the small m because it is at infinity distance from the central mass. So this statement comes from this fact that if you are at infinity distance, the gravitational potential energy must be zero. I hope this makes sense. Now, when object comes closer to central mass, its gravitational potential energy decreases. And if something decreases beyond zero, it becomes negative. Does this make sense?
Yes, sir.
Is it understandable? Like at infinite distance, there was no gravitational potential energy, but when we brought the object into the field, it means we have brought the object closer to the central mass. And if we bring something closer to the central mass, its gravitational potential energy is supposed to decrease. And if something decreases beyond zero, if something was zero and now it is less than zero, it must
Yeah,
be
yeah.
negative.
Yes, sir.
Okay.
Makes sense.
So now gravitational potential energy must be negative at any point. And let me explain that in one other way, because you are studying physics and this is very important for you to study. Like this is common for all the potential energies and all the potentials that we will be discussing later. So pay attention. In some cases there is a natural force acting. For example, if you bring a positive charge close to another positive charge, they repel, and that is natural. And if you bring a positive charge close to a negative charge, they attract. That is natural. If you compress a spring, it naturally tries to expand back to the original position. And if you stretch a spring, it wants to contract back to the natural position or equilibrium position. If you bring a north pole of a magnet close to another north pole of a magnet, it repels. And if you bring a south pole close to a north pole, they attract one another. So these are the kind of natural forces that are there. If like there's a rubber band, you stretch a rubber band, it will try to go back to the original position. Do you see some of the natural forces I'm talking about over here?
Yes, sir. Yes, sir. I understand.
Now listen, if you ever do anything against that natural force, against that natural, like the natural force of a spring is already stretched. So what is it naturally doing? It is trying to go back to the original position. But what happens if you stretch it more? It will have more potential energy. I'm not talking about stretching it beyond its elastic limit, but for example, if it is stretched by 1 centimeter, now you stretch it by 3 centimeter, what will happen? It is stretched more, so it will have more elastic potential energy because you are doing work against the natural force. Similarly, what is the natural force of gravity? Natural force of gravity is downwards. So if you do work against the downward force, like if you make an object go up, its potential energy should increase because you are working against the natural force. And if you let the object fall down, in that case field is doing work. That is work done along the direction of natural force. And whenever work is done along the natural force, potential energy decreases. A stretched rubber band has potential energy. A stretched rubber band has a potential energy. If you let it go, it will go back to the original position because in that case work is done along the direction of natural force. So what will happen
Yes, sir.
at the
In
end
this
of that
example.
situation? There will be no potential energy over there. So whenever work is done along the natural force, energy, potential energy decreases. As it is done in this case, when we are moving m from infinity to a point P inside the field, we are doing work in the direction of natural force. We are doing work in the direction of gravitational field. That means the potential energy should decrease because this is not the work done against the field, it is work done by the field. Whenever field is doing work, potential energy must decrease. But that is one Very sophisticated way of saying something, and examiner in A levels are happy to accept this answer when somebody says, because potential energy is zero at infinity and we are bringing it close, and when something comes closer to the central mass, its potential energy decreases, and when potential energy decreases beyond zero, it becomes negative. 100% marks. If it is a 2-mark question, you get 2 marks. If it is a 3-mark question, you get 3 marks, full marks. Okay, and this is examiner's FAQ. This is frequently asked question. This is his favorite question. He never gets tired of asking this. Okay, if you will open 10 past paper question, you will find this in more than 3 questions over there. Okay, 4 questions even. So this is a very common question. Gravitational potential energy. So we have done that. Now now for an orbiting satellite. For example, this is Earth, and this is a satellite. Why don't you make a normal elliptical curve like this? Okay. Now, so this is a satellite which is orbiting at a distance of r from the center, and this is the central mass m. The satellite has a mass small m. So here are the things. Centripetal force should be m v square over r. Gravitational force should be g m m over r square. Gravitational potential energy is minus g m m over r, and kinetic energy is 1 over 2 mv square. Now, what will be the orbital speed for orbital speed? We have already done that in previous lessons, but let's do it again. Now, for orbital speed, we will put centripetal force equals to gravitational force mv square over r equals to g m m over r square. And you have to make v the subject of formula. You can clearly see we can get rid of 1r on each side. There is r square on the right side. There's just r on one side. The r over here is dividing. If we shift it over there, it will get multiplied, and that can cancel 1r with 1r. And we can also cancel m with m. And we will left with v square equals to gm over r. So if we take square root on both sides, we will have v equals to under root v equals to under root gm over r, and this is the formula for orbital speed. Now, this is for orbital speed. If somebody wants to know how many meters or kilometers the satellite is moving in every second, you can find out using this formula. Now, if that is the formula for V, can we get rid of V from the kinetic energy formula? What will be the formula for kinetic energy if we install this value of V into kinetic energy? Let's see. Kinetic energy will become 1 over 2 m under root g m over r square. So we can simply cancel square with square root, and we have g m m over 2r. So this is the formula for kinetic energy. Pay attention, things will escalate from here. So what is the formula for gravitational potential energy? Minus gmm over r. What is the formula for kinetic energy? Gmm over 2r. What is the formula for total energy? Total mechanical energy of the satellite. That will be gravitational energy plus kinetic energy. It will be minus gmm over r plus gmm over 2r. So what will be total energy of the satellite?
Minus a half GHMM over R.
No, it's slightly wrong. Can you give it a try again? In order to make the denominator same, you can multiply the first fraction with 2 in the numerator and denominator. You can make it minus 2 gmm over 2r, and then you will have a common denominator. You just have to use the numerators then.
Yes, sir. Minus a half multiplied by GMM over R.
Yes, gmm over 2r with negative sign.
Yes, sir.
That is the total energy. Now, again, when you will see satellite questions, you will find out examiner is saying that a satellite was slowed down, satellite became faster, satellite um, lost energy, satellite gained energy, satellite, and there will be things happening to satellite. The radius of the satellite got smaller, the radius of the satellite got bigger. How will it affect? Now, pay attention over here. If like let's say that we are talking about radius increasing. Radius of the satellite increasing means satellite moving away from the surface of the central mass, in this case Earth. So look at this formula and tell me what will happen if R will increase. If we simply ignore the negative sign, if we simply like see that there is a double catch over here. Normally, when we see a reciprocal thing like this, that Eg is over there and R is in the denominator, we are 100% sure that gravitational potential energy is inversely proportional to R. So if R has to increase, potential energy has to decrease. But if we pay attention to that negative sign, it becomes the other way around. Oh, If R will increase, gravitational potential energy will decrease. A number that is with a negative sign decreasing mean actually it is increasing. Interesting. So that means if R is increasing, gravitational potential energy increases. So what happens to kinetic energy? Here we go. If R increases, what happens to kinetic energy? It is a straightforward positive relation. So very much like everything you've been doing till now. If R increases, kinetic energy decreases because R is in the denominator. Simple. What happens to total energy if R increases? Okay. What happens to total energy if R increases? If R increases, kinetic energy decreases, gravitational potential energy increases, and overall total energy also increases. Look at the negative sign again in the total energy. So total energy is very much like it. I'm not saying total energy is like gravitational potential energy. I'm saying that it will behave in this case like uh, gravitational potential energy. And with the increase of radius, total energy will also increase. Yeah. And it is difficult to say because we are looking at something in the denominator, and from deep inside our hearts we want to say that, you know, if R is increasing, the total energy should decrease. Yes, it like numeric value has to decrease, but it is coming with a negative sign, and when the numeric value with the negative sign decreases, actually the quantity is increasing. Interesting. So this is a very common question. Like when we will be starting solving question, you will find out that the um, uh, past papers are filled with them. Now, escape velocity. Escape velocity is a concept when the total energy has to become zero. Amount of there is always a value of kinetic energy that, if provided to an object at a point, it can escape the gravitational field it is in. Means, let's go back to the point that we brought into the field in the first place. Like for example, this point P. Is it possible to make it go back to the infinity again? In that case, how much energy we have to put in? So at this point, this object has a total energy minus uh, gmm over 2r. And in order to make it go to infinity, what should be the value of energy it should have? Zero. So we have to find out how much energy we have to provide it so its energy becomes 0. So look at the total energy. It is gmm over 2r. So if we provide exact this amount of kinetic energy, a positive kinetic energy, it should become 0. So required kinetic energy equals to gmm over 2r. And we know kinetic energy comes with formula 1 over 2 m v square equals to gmm over 2r. So 2 cancels with 2, m cancels with m. So but this will be the just 1 second. This will be the orbital velocity. Uh, let's see if this is the surface of Earth and there is this object and we provide it with kinetic energy that is so much that object can actually go to infinity. So its energy becomes 0. So if it has a gravitational potential energy of minus gmm over r here, and it has a 0 energy here, how much energy we need to add to this object so its energy becomes 0? So kinetic energy that we need will be 0 minus gmm over r, so 1 over 2 m v square equals to gmm over r. You can cancel m with m, and you can see that v equals to square root of 2gm over r. So this will be the velocity that if we provide to an object, it will go out of the field and will never come back. This is the velocity that we need to provide to something to make it go into infinity. Where v is escape velocity. Okay. So in the beginning, I was talking about total energy, but that total energy already had that kinetic energy in it. So that was incorrect. Actually, we have to equate it to the change of gravitational potential energy that we have to provide. So this will tell us the total kinetic energy that we need to give to an object in order to make it escape into the infinity. So tomorrow we will be doing change in gravitational potential energy and gravitational potential. So this is what we'll be doing tomorrow. Today, this is it. Yeah, let's call it a day. Thank you very much.
Okay, sir. Assalamualaikum. Have a nice day.
Walaikum salam. Allah Hafiz.